Okay, so we have three types of compounds. And nomenclature is a system of naming these compounds, and it's based on a system and not on just random names. Chemicals are not named in the same way that people are, where somebody just says, hey, let's call him Joe, and there's his name, and there's no pattern to it. It's a very systematic pattern. But there's different patterns for different groups of chemicals. And so there are, we have ionic compounds. We have ionic compounds. And each of these types of compounds has a different set of rules. And we have acids, and we have covalent compounds. Each has a different set of rules for naming them. And so the first step in naming it is to identify what kind of a compound is it. So for an ionic compound, the key is that you have almost always a metal and nonmetals. There might be just one nonmetal, there might be more than one. So if you look at the compound, and we learned a little bit about the order that the elements are put in a compound, the metallic one is always first, right? If they're both nonmetals, the more metallic one is first. So we looked at nitrogen and oxygen. If you have a compound between those, we put nitrogen first. They're both nonmetals, but nitrogen is closer to the metals than oxygen is. So the metal's going to come first. So all you have to do is look at the first element. If the first element is a metal, bang, it's ionic. End of story. Okay? So metal, if it has a metal in it, it's ionic. Acids are easy to recognize also. Acids are going to start with hydrogen. So if you see a formula and it starts with H, you know it's an acid. And then you have to use the acid rules. And we're not going to do the acid rules and the covalent rules. We're just going to do the ionic rules today. There are some acid and covalent ones in this lab, but we're just going to do the ionic ones because that's the ones people have most trouble with. And we'll figure out the rest of them next week. Covalent compounds are two nonmetals. And they have their own set of rules. If it's three nonmetals, it's going to be something else. Exactly two. Two nonmetals uses the covalent compound rules. Okay? So what we're going to do today is we're going to learn how to name and how to write the formulas for the ionic compounds. So let's see, I think I can go to, there's another slide. So in this lab, on page 55 and 56, they list out many of the common positive ions and negative ions. And we talked about this a little bit in lecture. So today when we're doing the lab, feel free to refer to these lists of positive and negative ions. But just know that I'm not going to give these to you on an exam. Darn it. If we look at the list of positive ions, many of them, their name is just the same as the element name. So for example, potassium ion is K+, and its name is potassium. I left out the I, we'll squeeze it in there, potassium. But some of them, like iron, Fe2+, its name is not iron ion, it's iron with the Roman numeral 2. And so if you look at those, some of them have a Roman numeral and some of them don't. And so there is a pattern behind this. We looked at the periodic table a little bit and talked about the charges that the different elements form when they make ions. And so what we said was the metals always form cations. Metals make cations. The group 1 metals form +1 ions. Group 1A or group 1, those make 1+ ions. The group 2 metals, what charge do they form?
+2.
+2.
2+.
So group 2 makes 2+. Group 3 makes
3+.
3+. See that? It's group 3A or group 13, depending on how your periodic table's numbered. And there's a couple of other ones that we can just know, and we won't worry about them today. The rest of them, most of the rest of the metals are in the transition metals, the transition elements, that sunken down part of the periodic table. And if you look at the ones on this list that have Roman numerals, and you find them on the periodic table, they are not in group 1, 2, or 3. They are either a transition metal or they're over on the side in group like 14, 15. Lead and tin, those guys are a little over on the side. The reason we need a Roman numeral for these guys is they can form more than one kind of ion. Iron can form a +2 ion, and it can also form a +3 ion. And there's no way to tell from the periodic table what they're going to do or which element, which of those two ions it's going to be. Okay? So they're kind of squirrely and unpredictable. So in the name, we have to indicate to the reader which charge the ion has, and so we use the Roman numerals to do that. So iron 2 is going to be iron with the Roman numeral 2, and iron 3 is iron with the Roman numeral 3. Ran out of blackboard there. So look at that list, like lead 4, lead with the Roman numeral 4, the charge on that is 4+, Pb 4+. Bismuth 3, there's a Roman numeral 3, the charge is 3+. You see that pattern? If we look at something like aluminum, aluminum doesn't have a Roman numeral. But if we find it on the periodic table, it's in group 3. It has a 3+ charge. Okay, so that's how we know the charges on the metal ions. Group 1, 2, or 3, it's +1, +2, or +3. The others are going to have Roman numerals that tell you. So if you look at the name, it's got a Roman numeral that tells you the charge. Okay? Any questions about the cations? So let's talk about the anions, the negative ions. The nonmetals form negative ions. Non-metal, negative, they both start with N. So the nonmetals form anions. And their charges are predictable from the periodic table. So this was where we played that, like pretending we were playing a dumb board game on the periodic table. And you count backwards. The noble gases are in the far right column. They don't form ions. They form hardly any compounds. They're fine. They don't need to share electrons or transfer electrons or do anything like that. And we'll understand more why that is later. But for now, we're just going to look at the patterns. Yeah, I wish I could just pull up a periodic table on here, but I don't know, I can't do that. So group 8 doesn't form ions. The far right column, their charges would be 0. They don't form ions, and so we'll not encounter them in this lab today much. So if we go one to the left, like you're playing a board game, you're starting on the right and you're moving back a square, everything in column 7 has a -1 charge. So group 7, group 7A, also numbered 17, those all form -1 ions. Fluorine, chlorine, bromine, iodine, they all have a -1 charge. We go to the next column over. You did this to me yesterday. I don't know why it does that. If we go to group 6A or 16, those all have a 2- charge. Group 5A, group 15, those all have a 3- charge. So the explanation most students seem to like is just count backwards from the far right. -1 square, -2, -3, that's the charge on that element. What it really is they're trying to get 8 electrons. The number of electrons that they have by themselves in terms of the outer shell, which we haven't talked about, the valence electrons, is the same as the group number. So in group 5A, they have 5 electrons on the outside. They want 8. They need 3 more. Hence, they get a -3 charge because they'll tend to gain 3 electrons. That at this level, and at this point in the semester, that's not a very satisfying answer. And then we need to know about the names of these. So, like, let's do bromine, the ion. To write the name of this ion, we take the element name, bromine, and we take off this last part, and it becomes bromide. That's the ion. And so you take the element name and you change the ending. We do a lot with prefixes and suffixes instead of just inventing new words. So like oxygen is in group 6A, it forms a 2-. Oxygen, the name of the ion is oxide. Phosphorus forms a 3- ion. Phosphorus is the element name. The ion name is phosphide. Does that make sense? So chlorine becomes chloride, sulfur becomes sulfide, nitrogen becomes nitride. And we get the charge of that ion from the periodic table. Then we have polyatomic ions. Polyatomic ions have many atoms. Polyatomic means many atoms. Polyatomic. And some of these I made you guys memorize, right? The ones that end in 8. And so I told you, well, you need to memorize that NO3- is nitrate ion. And ClO3-, oh, it's okay, it just glitched, is, what's the name of that one? ClO3-, chlorate. What most of those polyatomic ions have in common is that they're a nonmetal combined with oxygen. So they're also called oxyanions because they're anions and they have oxygen in them. The oxyanions are going to have a suffix of 8, the ones I made you memorize. And then there are some others that are related. So, let's see. Yeah, I can fit it all on here. So let's put chlorate on here. So there's chlorate. You memorize that one. And then there's another one that's ClO2-. The difference between those two is what?
A negative charge? One negative.
Well, they both have one negative charge. One has 2 oxygens, one has 3 oxygens. So these are related to each other, and yet they're not exactly the same. This one is chlorite. What's the difference between Bud and Bud Light? Less calories, right? Bud Light has fewer calories. Chlorite has fewer oxygens than the regular chlorate. Does that make any sense? It's the light version, ITE. Chlorate, you just memorize that one. You already did that. Chlorite, same charge, one less oxygen. You like that? Yeah.
I like the beer one.
The beer one, yeah.
That's all I remember.
Right, you know. And thankfully nobody said, well, Bud Light tastes horrible. I don't know, I don't drink beer. We can also go one less even than the light version. This is hypochlorite. You've heard of a hypodermic needle, right? Dermic refers to your skin, your dermis. Hypodermic means it goes below the skin. Hypo is a prefix that means below or less. So hypochlorite is even fewer oxygens than the light version. There's a pattern here. Okay, so you memorize this one, and then you learn the pattern, and you also know a whole bunch of other ones. Then there's also one that's got more oxygen. There is ClO4 minus. And that one is called perchlorate. So we've got these, there's a prefix and a suffix and this prefix. A hyper person, do they have more energy or less energy than a regular person? They have more. Hyper, or per for short, means more. Hypo is less, hyper is more. Hyperchlorate has more oxygen than chlorate. So there's this pattern going on here. So let's do some examples. Let's do sulfate. What's the formula for sulfate?
SO4 2 negative.
SO4 2 minus. So that's sulfate. What would be the formula for sulfite?
SO3 2 negative.
SO3 2 negative. So you had the 8 memorized, and then we learned a pattern, and we can write the names of the other ones. Now, not all 4 of those exist for every oxyanion, but you don't need to know which ones exist and which ones don't. Okay? We'll just memorize the pattern, and we'll use it whenever we're presented with something. So that's not one I made you memorize. But if we remember that elements in the same column are like people in a family and they have similar characteristics. Like I have 5 boys, and so far 4 of them are playing football. And the 4-year-old would play football, but there's no tackle football leagues for 4-year-olds, so he's just got to wait until he grows up a little bit. But they have that thing in common that they love football. Okay, they're brothers. So if we look at the periodic table, iodine is in the same family as chlorine, right? It's going to form similar oxyanions to chlorine. If this was ClO3 minus, it would be named what?
Chlorate.
Chlorate. So what do you think this one's named?
Iodate.
Iodate. And we can do the same thing for bromine. BrO3 minus would be bromate. So there's iodate. Then what's this one? Periodate. Okay? So I think you're seeing the patterns going on here. It's going to take some practicing, though, for them to stick in your head. There are other polyatomic ions that you just have to memorize. Hydroxide, peroxide, cyanide. Those guys don't really follow a pattern. There's one other little pattern that we kind of run into sometimes. Oops, that's not a 3. What's PO4 3 minus? That's phosphate. I don't know, did I ask you guys to memorize that one?
I think so.
So phosphate is PO4 3 minus. Now this guy, yeah, it's not per. So the per 8 doesn't mean 4 oxygens. It's relative to what the 8 is. So some of the 8s are O3, some of them are O4. You have to learn that one, and then you can build others in relation to it. And it has nothing to do with the charge, but the related ions have the same charge, all they differ in is the number of oxygens. But what's the difference between PO4 3 minus and HPO4 2 minus?
It's an acid?
It might look like an acid because it starts with an H, but it's an ion because it has a charge. The difference is that the HPO4 has a hydrogen on it, right? If we look at the periodic table and remember that hydrogen's the baby brother of the elements and he's an exception to everything, he's over in group 1. So what kind of an ion might he form? +1. Okay, and what is weird about that? Is hydrogen a metal? No, it's a nonmetal. And yet hydrogen can form a positive ion. Right? Because the baby brother gets away with stuff that the firstborn never got away with, right? I'm the firstborn. But I'm also letting the baby brother get away with murder sometimes. Because I'm old and I'm tired. And that's why your parents did it too. Hydrogen can form a positive ion or a negative ion. It usually forms a positive ion. So PO4 3 minus and HPO4 2 minus, the charge is different by 1. And there's a hydrogen on the HPO4. Well, that's because it's an H plus on there. If you put an H plus with the 3 minus, those add together and give us a 2 minus charge.
I lost the screen.
Oh, lost the screen again? Stupid thing. Thank you. So that gives us a 2 minus charge instead of a 3 minus charge. But this guy needs a name. And so his name is hydrogen phosphate. Write it up here. Hydrogen phosphate. Real creative, huh? It's phosphate with a hydrogen ion stuck on it. So if you'll look at these, there's hydrogen phosphate, there's dihydrogen phosphate. And then I don't like this, on page 57, they show bisulfate and bisulfite, HSO3 minus and HSO4 minus. They also sometimes put the prefix bi on there when there's a hydrogen ion on there. So that is used, but I prefer not to use it. I would prefer to call those hydrogen sulfate and hydrogen sulfite. And above that is bicarbonate. So this is carbonate, CO3, 2 minus is carbonate. And HCO3 minus is hydrogen carbonate. And so those are the words, those are the names. Yeah, whoops, that's not what I want either. Come on. Hydrogen carbonate or bicarbonate. There are some old names that just persist because people are so familiar with them. Have you heard of bicarbonate of soda? That's baking powder. I'm sorry, baking soda. Baking soda. Bicarbonate of soda. It's sodium hydrogen carbonate is what it is, or sodium bicarbonate. So you will come across what it means is that there's a hydrogen ion on there. But I'm going to use the hydrogen ion version. If we have two hydrogens, like H2PO4, it's dihydrogen, H2PO4, and then it's just going to be -1. That's dihydrogen because it's got two hydrogens on it. Dihydrogen phosphate.